Welcome to an example on how to solve an initial value problem involving a linear first-order differential equation. We'll be solving the differential equation using an integrating factor. The first step is to make sure the differential equation is in the correct form, where the correct form is given here, where we have dy dt plus p of t times y equals f of t. Comparing this form to the given differential equation, notice how the equation is not in the correct form. This term is the function of t times y, so we need to subtract this on both sides so it's on the same side as dy dt. So the given differential equation can be written in the form of dy dt, and then for the fraction, to make it more obvious that it's a function of t times y, let's write this as minus 1 over the quantity t plus 1 times y, and then equals 4t squared plus 4t. So again, we have dy dt. Here we have a function of t times y equals a function of t. Step 2 is to find the integrating factor, which is mu of t equals e raised to the power of the integral of p of t dt. So notice that p of t is negative 1 over the quantity t plus 1. So the integrating factor mu of t is equal to e raised to the power of the integral of negative 1 divided by the quantity t plus 1 dt. This will give us e raised to the power of negative natural log absolute value of the quantity t plus 1. We can also think of this as negative 1 times the natural log. So for the next step, we'll apply the power property of logarithms and move this negative 1 to the exponent position of the quantity t plus 1. So here we'd have e raised to the power of natural log absolute value of the quantity t plus 1 raised to the power of negative 1. From here, because we have base e here, and the exponent is natural log or log base e, this simplifies to just the absolute value of the quantity t plus 1 raised to the power of negative 1. And because we're told t is greater than negative 1, we can drop the absolute value, and to make the exponent positive, we can write this as 1 divided by the quantity t plus 1. So the integrating factor is mu of t equals 1 divided by the quantity t plus 1. Step 3, we multiply both sides of the differential equation in this form by the integrating factor. So we'll have mu of t, which is 1 over the quantity t plus 1 times dy dt minus 1 over the quantity t plus 1 times mu of t, which is 1 over the quantity t plus 1 times y equals 1 over the quantity t plus 1 times, let's go ahead and factor 4t squared plus 4t, that'd be 4t times the quantity t plus 1. And now we'll simplify. So we have 1 over the quantity t plus 1 dy dt minus 1 over, here we'd have the quantity t plus 1 squared times y equals, on the right side, notice how t plus 1 divided by t plus 1 would simplify to 1, so the right side simplifies to 4t. For step 4, this left side is now equal to the derivative of the product of mu of t and y. So this left side equals the derivative with respect to t of mu of t, which is 1 divided by the quantity t plus 1 times y. Of course, we can check this. To find this derivative, we'd apply the product rule, where we'd have the first function, 1 divided by the quantity t plus 1, times derivative of the second function, which is dy dt, plus the second function, which is y, times the derivative of the first function, which is 1 divided by the quantity t plus 1, which is negative 1 divided by the quantity t plus 1 squared. So the last step to find the general solution is to integrate both sides of the equation and then solve for y. Once we find the general solution, we can use the initial condition y of 1 equals 5 to find the constant of integration, which will give us the particular solution for the initial value problem. Integrating both sides, we'll have the integral of the derivative with respect to t of 1 divided by the quantity t plus 1 times y dt equals the integral of 4t dt. Let's integrate on the next slide. On the left side, the integral and derivative undo each other, and therefore we're just left with 1 divided by the quantity t plus 1 times y. We would have a constant of integration, but we'll include that on the right with the constant of integration from this integral here. So we'll have equals, the integral of 4t with respect to t would be 4 times t squared divided by 2, which would be 2t squared and then plus c. Now to solve for y, we'd multiply both sides of the equation by the quantity t plus 1. So notice on the left side, these factors simplify to 1. So we're just left with y, or y of t, equals, on the right side, we'd have 2t squared times the quantity t plus 1 plus c times the quantity t plus 1. So this would be the general solution to the differential equation. We want to find the particular solution using the initial condition y of 1 equals 5. So we'll substitute 1 for t and set y of t equal to 5, which will allow us to find c, the constant of integration. So performing the substitution, we'd have the equation 5 equals 2 times the quantity 1 squared times the quantity 1 plus 1 plus c times the quantity 1 plus 1. So simplifying, we have 5 equals, here we'll have 2 times 1 times 2, that's 4, plus, here we have 2c. So subtracting 4 on both sides, we have 1 equals 2c. Dividing both sides by 2, we have c equals 1/2. Now substituting c equals 1/2 in the general solution, we would have y of t equals 2t squared times the quantity t plus 1 plus 1/2 times the quantity t plus 1. Notice how these two products contain a common factor of t plus 1. Let's go ahead and factor out the common factor of t plus 1. So we'd have y of t equals the quantity t plus 1 times the quantity 2t squared plus 1/2. Let's go ahead and leave the particular solution in this form here. So going back to our first slide, the particular solution to the initial value problem is y of t equals the quantity t plus 1 times the quantity 2t squared plus 1/2. I hope you found this helpful.